Hello. My break was fantastic. Hello. Gonna wait till we get to 20 viewers. Almost there. Hope you guys had a nice vacation. I will ask you about it in the Zoom room. All right, we're over 20, so I'm gonna get started. So today, uh, oh my gosh. I actually had a really good night's sleep last night, so I feel pretty good. Um, so what we're gonna do now for the next few weeks is you guys are going to be working on your IAs, um, and I will be going over some of the non-programming topics that are part of the IB computer science curriculum, and and I'll still be having, I think, one assignment per week. That assignment will be may or may not be a programming assignment. Okay, so for this week it is, but I don't know about next week. I haven't gotten there yet. Um, your midterm is available now, your second midterm. So that is due on next Monday. And yeah. So the first topic. Now, by the way, I found an IB computer science textbook um, that I'm trying to see if I can pull up the first page here, just so you can see. Um, it's on my phone. Core Computer Science is what it's called. It's by like Dimitriou and Hatzitascos. Um, this is like the only IB computer science book out there, and so I downloaded it on the internet. It is out there. You can find it, and you can read it if you want to. So this lesson is inspired by a chapter I read in this textbook. Okay. Um, so what we're going to talk about today is computer organization first, and then binary numbers. second. All right. So computer organization. So this is what we're talking about today. So this is what IB wants you to know about computer organization. So this is going to be a very simple computer. It does not have any peripheral devices such as graphics cards, things of that nature. Okay. So sort of the simplest model of a computer is that it has an input, which is from the user, and it has an output, which is to the user. Okay. And so what we have here is we have, maybe I should zoom out more so you can see the whole thing. Okay. So there's three things. There's CPU, which stands for Central Processing Unit, which is basically the brains of the computer. All right. And then you have memory. Okay. And so these are both just memory. There's a primary memory. Okay. And then there is a secondary memory. And so I'm going to talk about the difference between those in a moment. Okay. So let's go ahead and talk about what's going on inside the CPU. Okay, what does the CPU have? And so I've abbreviated some of these different components. So first of all, we have CU. CU stands for Control Unit. Okay. And what the control unit does is it fetches, so it fetches instructions and data from the memory. Okay. Fetches instructions and data from the memory. And then tells the rest of the CPU what to do with it. Okay, so for example, if you want to add a number, okay, to another number that's in memory, the control unit is going to get that number from the memory and then tell the rest of the CPU, hey, we're supposed to add these two numbers together. Okay, so it's all right. Now it has the control unit within it has two parts, MAR and MDR. Okay, so that MAR is called the memory address register. So a register. Now I actually dealt with registers because I got a minor in electrical engineering, so we talked a little bit about registers. And so a register is basically just a really small memory, okay, that stores stuff. It's almost like a notepad, it's just for storing a little bit of information that you're going to need. So generally in hardware, the larger the storage is, the slower it's going to be to access what's in that memory. Okay, so it's really small, but it's lightning fast. Okay, and the memory address register holds the addresses. And when I say the address, I mean the location in memory, because it's got to find, the memory just has a bunch of ones and zeros, so you have to know where to look. Okay, holds the address of instructions and data. Okay, so I mean the control unit doesn't even know how to add things together. It has to look up the instruction to add. Okay, so it doesn't really know what it's doing, but it just knows how to look for the next thing. Okay, so it holds the memory address of instructions and data. MDR stands for memory data register. Okay, so the memory address register holds where the instructions and data is, and the memory data register holds the actual data. Okay, so in some sense, the memory address register is sort of ahead of the memory data register. Okay, so the memory address register says, okay, get the data that's stored in memory address 1. Okay, and later on that will appear in the memory data register. Okay, the instructions, it goes both ways. So also, once the CPU does some processing, the memory address register could store where the data is going to go, and then the memory data register holds what should be written to that particular location. So these registers can hold both things that are coming from the primary memory and things that are going to the primary memory. Okay. The ALU stands for arithmetic logic unit. And basically what the ALU does is it does additions, multiplications, Boolean operations such as and or not. So I'll just say logic operations. Okay, so it actually processes the data that the control unit gives it. If you have like a graphics card is essentially a peripheral device that has an arithmetic logic unit that is lightning fast. So you're basically paying for a specialized arithmetic logic unit that's really good at doing the types of computations that are needed for graphics. So it's specifically designed to do certain types of computations in a very fast way. Whereas, your general CPU is going to be able to do, it's not specialized. It's for general computation. Graphics processing it's specifically designed to do one thing very fast. Okay. So then we have the primary memory. Okay. And one of the things about memory is that it is hierarchical. Okay, so we have memory that is close to the CPU and memory that is far from the CPU. So the memory that is farthest from the CPU is the secondary memory, and it's almost like a pyramid. Okay, the memory that is closest to the CPU has the least amount of storage, but it is the fastest. And as we go progressively further away from the from the CPU, we get more and more storage, but it becomes slower and slower. Okay, so the very first thing we notice is that there are these two things called caches. So there's a level 1 cache and a level 2 cache. And the caches are basically really fast, really small memory. Okay. And there are basically, okay, so it's made up of something called static RAM, SRAM. And SRAM is the fastest form of RAM, but it is really expensive. So basically what computer designers have done to minimize the cost of the computer is they just give you a little bit of memory that's of this fastest form, okay? All right. And that's for both the level 1 and the level 2 cache. Now those caches are connected to each other through the data bus. So the data bus is there to transfer data from in between the CPU and the primary memory. And the memory bus, so a bus is basically just a bunch of wires, okay, that are transmitting data. The memory bus sends memory addresses back and forth, okay? And then we have our primary memory, okay, which is RAM, but a slower version of RAM called DRAM, okay, which stands for Dynamic Random Access Memory. So it's very fast, but not as fast as static random access memory. Okay. And so it's, most computers might have, I don't know, a gigabyte or two. Someone type in, how much RAM do you have on your computer? Let's see. Someone type it in the live chat. I want someone to flex. Okay. Ooh, 16 gigabytes. Ooh. Okay. I think my computer has like 2 gigabytes of RAM, something like that. So we'll talk about why. What is the most RAM that could you get 32 or 64 gigabytes of RAM? I'm curious. Okay, so then you have, so this RAM is just a general purpose storage. It's stuff that the CPU is going to need often. Okay, so wow, terabyte. That's crazy. So then you have ROM, which stands for read only memory. So the thing about RAM is it can be overwritten. So stuff can be transferred to RAM. But if it's a read-only memory, that memory was written by the manufacturer, and it doesn't change after that. Okay? So basically, your ROM is going to hold startup information for your computer. Okay? Because that's not going to change. Every time you turn on your computer, it's going to start up in the same way. All right? So it's read-only memory. Now, what is the difference? So RAM, you can rewrite. ROM, you cannot rewrite. The other thing is that RAM is what's called volatile. Okay? Also called non-persistent. And so what that means is that when the power of your computer is turned off, whatever is stored in the RAM is forgotten. Okay? So, for example, if you are typing in a word processor and you don't save it, nowadays everything just saves automatically, but if you, let's say you had an old word processor that didn't save automatically, if you're typing in, it's storing that stuff in the RAM. And if you turn your computer off without hitting save, it never gets transferred to persistent memory. And so when you turn the computer back on, those changes won't be reflected. Okay? ROM is non-volatile, also known as persistent, which means that the information is saved even when the power is cut. Okay? So then you have your secondary memory. And your secondary memory is slower. It is much more storage. Okay. And then it is also going to be non-volatile. So for the secondary memory, you want to think about like your hard disk. Okay. So that memory is saved even when the computer is powered down. So one of the things that has to happen, okay, when you turn on your computer, okay, your operating system starts to run. So I don't know, Mac OS X or Linux or Microsoft Windows or whatever. And part of what's happening is that stuff is being transferred from your secondary memory into your RAM. Okay? So that's part of what's happening on startup of your computer. Okay? So what you have to have is you have to do this thing called memory management. Okay, so what is memory management? Basically, your computer is trying to strategize, okay? It doesn't make sense to store information that you're going to be using frequently in the secondary memory, okay? So what happens is if you start up a program, so let's say Adobe Photoshop, your computer is going to transfer Adobe Photoshop's information from the secondary memory into the RAM because you started that program, so the CPU knows that you're going to be needing that data often, so it transfers it into the RAM in order for it to be quickly accessible. Okay? So that's called memory management. It's trying to put the stuff that it thinks you're going to need into the RAM. Now, what happens if you are playing Photoshop and, I don't know, Microsoft Word or something like that, and your RAM is full, okay? If your RAM is full, your computer has to do what is called swapping. And so let's say I'm using Photoshop, and Photoshop is taking up all of my RAM, okay? Then I click over to the next window over, and I'm using Microsoft Word. So now what the computer has to do is it has to remove Photoshop from the RAM and fill it with Microsoft Word. And that takes time to transfer from secondary memory to RAM and back and forth, okay? So this is one of the reasons why when you switch programs, you have a sort of a delay occurring. Okay, it's because your computer is switching information between your secondary memory and your RAM. So this is why it's advantageous to have a lot of RAM, because the more RAM you have, the less swaps you have to make, and so your computer will run a lot faster. But the downside is RAM is, of course, volatile, and it's also expensive. Wow, $1,500 for 128 gigs of RAM. That's ridiculous. So basically, your operating system is going to do all of this management. I want to talk about the instruction cycle. So what is happening within the control unit? So basically, the control unit is going to fetch the instruction. Okay, now the instruction is stored either in the RAM. The next instruction is stored somewhere in the RAM. Then it's going once the control unit gets that instruction. So maybe add 2 numbers. It then knows that it has to look for those 2 numbers. So then it fetches the data. So once it knows what the instruction is, it knows what information it has to get. And then it's going to do the computation. So that's typically going to be handled by the ALU, the arithmetic logic unit. And then after that, it's going to write the data to the RAM. Well, actually, what happens is it would write it to the cache, the level 1 cache, then the level 1 cache would write it to the level 2 cache, then the level 2 cache would write it to the RAM, and then eventually it would go to the secondary memory. So, and then this repeats. Okay, so each of these steps kind of takes a set amount of time. So when I was, I think that the clock speed of your computer has sort of plateaued. I don't think that clock speeds are getting any faster. Maybe someone can fill me in on this. Like, I can remember getting a 500 megahertz computer. I can remember when megahertz was the fastest clock speed. Now I think it goes up to, I don't know. Do we have terahertz processors yet? I don't even know. I think we're in the hundreds of gigahertz. I'd be interested to hear what your guys' computers, what their clock speed is. But so that's sort of plateaued, it seems like. But anyways, each of these steps is going to take a certain number of clock cycles within your computer. Okay, so the more clock cycle, the faster your clock speed is, the more quickly you can run through the instruction cycle, and the faster your computer runs. Okay, so this is a little overview of how a computer works. Okay, this is a very simple computer. If you have peripheral devices like graphics cards, monitors, things like that, then there's also going to be some communication between the CPU and those peripheral devices. Okay, so it might be sending output data or getting input data from those peripheral devices. All right. So now we want to talk about how is data stored in the computer. And so basically it is stored as ones and zeros. So so we have, of course, a binary digit is a 1 or a 0, which is called a bit. Okay, so it's stored in bits. 8 bits is 1 byte. 8 bits is 1 byte. All right. So these are common terms in computer science. Okay, so in particular, I want to talk about numbers. How are numbers stored in your computer? And today we're just going to talk about positive numbers. Next time we'll talk about negative numbers. Okay, so let's think about a base 10 number system. So let's say I have the number 2,958. All right. So this would be the ones place. This would be the tens place. This would be the hundreds place. And this would be the thousandths place. Okay, so one of the things I want to point out is that the ones place is 1 is 10 to the 0, 10 is 10 to the 1, 100 is 10 to the 2, and 1,000 is 10 to the 3. All right. All right. So, and then if you think about the digits, a single digit within your base 10 number, okay, can go from 0 to 9. So the largest individual digit is 9. Okay, so it turns out that in a base 10 number system, this can be written as 2 times 10 to the third plus 9 times 10 to the second plus 5 times 10 to the 1 plus 8 times 10 to the 0. So if you just work that out, that's 2,000 plus 900 plus 50 plus 8. All right. So the reason that the digits can only go from 0 to 9, okay, is because when you do that, you don't have any carrying happening here. Okay, when you add these three numbers together, it's going to be 2,000 plus 900 plus 50 plus 8. So we can see that when we add these two up, when we add, we're not going to have any carries because 8 is added to all zeros, okay? If I allowed the digit to go up to 11, so if I had 11 times 10 to the 0, then I would have to carry over to the next column. So basically, when you follow these rules, a number can be written uniquely in this form. So there's only one way to write a number like this. Okay? So let's try to generalize. What if you have a base k number system? Base k number system. So let's call that base k number system. Let's say A0, A1, A2, A3, A4, dot, dot, dot. Okay? So these, and then we'll put a subscript k behind it to indicate the base of the number. Okay, so maybe we can put it all in parentheses. If you were at base k, each individual digit can go up. What is the largest value that an individual digit can go up to? All right? Who can generalize? Type it into the chat if you can generalize. If in base 10, the individual digits can go from 0 to 9. If you're in base k, what can the individual digits go from? Not quite. 0 to k minus 1. Excellent. 0 to k minus 1. Okay, so just like in base 10, it can go from 0 to 9. If you're in base 2, which is the binary number system, you can go from 0 to 1. That's why it's 0 or 1. Okay? So if this is the ones place, who can generalize? What place is this? This is the what place? And what place is this? And what place is this? And what place is this? Etc. Okay, no one's typing it in. So this would be the k's place. The ones place is the k to the 0 place. This is the k to the 1 place. This is the k squared place. This is the k cubed place. This is the k to the 4th place. So for example, if we were talking about binary numbers, this would be the 1's place, the 2's place, the 4's place, the 8's place, the 16's place, and so on. So it just completely generalizes what we've learned in base 10. Okay? So this number could be written as a to the 4th times k to the 4th plus a to the 3rd times k to the 3rd plus a to the 2nd times k to the 2nd plus a to the first times k to the first plus a to the 0 times k to the 0. Okay? So this tells us, this rule tells us how to convert from base k to base 10 really easily. Okay? Okay? So I want to talk about converting from base k to base 10. Here's how you do it. So let's say I have a number. Let's say it's 4, 1, 0, 3. And this is a base 5 number. Okay? So what does that mean? Okay, what is this equal to in a base 10 number system? Well, we're going to use this sort of expansion to put it into base 10. Okay, so this is the ones place. So it's 3 times 5 to the 0 power. And then plus 0 times 5 to the 1 power. So the 5's place has a digit of 0. What comes after the 5's place would be the 5 squared's place, which is 25. So we have plus 1 times 5 squared. And then we have plus 4 times what comes after the 25's place is the 125's place, 5 cubed. All right, so 5 to the 0 is 1, so we get 3 times 1 plus 0 times 5 plus 1 times 25 plus plus 4 times 125. So we get 3 plus 0 plus 25 plus, that's going to be what, 250 times 500. So this is 528 in base 10. So we've converted a base 5 number to a base 10 number. All right? So how do we do the reverse? Need a new piece of paper. Okay. Let's say we want to convert from base 10 to base k. All right. And so we're gonna pick an example. So let's say I have the number 546 base 10, and I want to convert to base, let's say base 3, for example. Okay, so what you're going to do is you are going to repeatedly divide by 3. Okay, so if I do 546 divided by 3, I get, so I'm going to divide 546 by 3. And what I get is 182, remainder 0. So how could I do this in programming? Well, when you're programming in Java, to get the remainder, you use the modulo operation. So you do you would do 546 mod 3. That's going to tell you the remainder. Okay. Division of integers in Java truncates the remainder. So that this would just be 546 divided by 3. So now what we're going to do is we are going to plug this in and we're going to divide that by 3. We're going to do 182 divided by 3. And that equals 60, remainder 2. Okay, so again, how did I get the remainder? You would do 182 mod 3. Okay, as computer code, because modulo gives you the remainder, and then just regular division gives you the integer part. Okay, then I'm going to take that and I'm going to divide by 3. So you have 60 divided by 3, and that's going to equal 20, remainder 0. Okay. And then I'm going to plug that in. I'm going to do 20 divided by 3. And this equals 6, remainder 2. Okay. Then I'm going to plug that in. I'm going to do 6 divided by 3 is 2, remainder 0. And then I'm going to do one last step, is going to be 2 divided by 3. And that's going to be equal to 0, remainder 2. So you keep going until you get to 0. So once you have 0 remainder something, you stop. Okay? And then you just read the digits going in that direction. So it's going to be 0, 2, 0, 2, 0, 2. Okay? And that would be 546. 546 in base 10 is equal to 202020 in base 3. Okay? What if we want to put it in base 2? Let's just go through the same process. So the algorithm is exactly the same. So what if we do convert to base 2? So instead of dividing by 3, we're going to divide by 2. All right. So 546 divided by 2 is equal to 273, remainder 0. Then I do 273 divided by 2. That's equal to 136, remainder 1. 136 divided by 2 is 68, remainder 0. 68 divided by 2 is 34, remainder 0. 34 divided by 2 is 17, remainder 0. 17 divided by 2 is 8, remainder 1. 8 divided by 2 is 4, remainder 0. 4 divided by 2 is 2, remainder 0. And then 2 divided by 2 is 1, remainder 0. And then 1 divided by 2 is 0, remainder 1. So I've reached 0. So now I go down and I look at all the remainders, and that's the digit. So I have 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So there you go. So your programming assignment for today, and this is the only assignment for this week, is to convert from base K to base L. All right, so that's my lesson for today.